Hello all, we are Team Vision Vanguards. The problem statement ID we've chosen is 1535, which is student innovation. The theme we've chosen is smart vehicles. Basically, it is about creating intelligent devices to improve commutation sector. In an era where technology is taking new terms every day, transport has become a necessity, commute has been playing a prominent part in our lives, and safety has become a concern. So our idea focuses on safety of commute sector because commute sector takes up a major amount in our daily lives, like going to gym, office, or to workplaces. So why us? Why smart commute? We have a couple of features which resemble our uniqueness. One is geofence. Geofence basically creates a virtual boundary around a specific area. So when the vehicle enters or leaves that specific area, we will be getting an alert. And one more is we can monitor multiple assets in a single app. In, for example, in commercial use, consider a warehouse and the vehicles has to go to different units. So these all vehicles can be monitored using a single app, or consider in domestic purpose where the daughter has to go to college or the parent has to go to office in four wheeler. These all vehicles can be monitored at a time in the same app. And one more is customization alerts. You can set up your own alerts of speed or sudden speed drop or other features provided. And dynamic data can be obtained through IoT sensors here. Our idea mainly focuses on geofencing. This because this is both useful in both commercial and domestic aspects. For example, consider me. Like I'm going to college in my two wheeler, and maybe I forgot my phone. So, in order to indicate that I've reached the college and I'm safe, geofence will be useful so that it will be sending an alert to my parents. Or maybe another case where my father is going to office and I'm going to college, and we want to monitor each other simultaneously without disturbing. So, in this case, geofence will be useful. In commercial aspects, the drivers reaching to the warehouses and starting from the location, this all can be monitored, and this even reduces the drivers for the personal use. Further usage of hardware sensors will be explained by Akhil.
So yeah, coming to a hardware prototype, we actually use Woki platform, which is an IoT simulator, which is used to make IoT devices virtually. And yeah, I have made the circuit with the potentiometer and using ESP32, which is Wi-Fi module and potentiometer. I have used for the ideal speedometer kind of. So yeah, and so how we are gonna get the speed of the vehicle? So I have mapped the potentiometer values, which the where the potentiometer values are 0 to 4096, and I have mapped using the map function, which is available in the platform, and I have mapped it to the 0 to 200, which is ideal vehicle speed as per consent to our prototype. And this is the one thing our hardware component does. And coming to the other thing, which is consumption rate of the fuel when the vehicle moves from particular speed, say 0 to 100, 100 to 150, and 150 to 200, and 200 constantly. So yeah, I have declared the fuel tank capacity, which is 45 liters, and I have declared 1% reduction rate of fuel when the vehicle constantly moving from 0 to 100 kilometers per hour. And same for 100 to 150, which is 2% reduction in fuel, and 150 to 200, which is 3%, and constantly maintaining a 200 speed, which is 5%. So I have uh, declared the consumption rate for 1 minute. So you can see when I run this component, you can see the fuel consumption metrics showing up. And coming to the third feature, which is overspeeding alert. Overspeeding alert when the vehicle reaches, or when the vehicle exceeds 100 kilometer per hour, which is declared by us say this is the limit where one can travel in the roads or traffic roads or on the highways. So the fleet manager or the personal vehicles or the parents of the children gets a notification where your child or your driver is overspeeding at each time at this road. So yeah, uh, I have used the if statement for this alert. So let me run it. Yeah. So this is basically prototype for when we are implementing it in the finale. We are actually making the component and we are running this device and the vehicle speed to a website. We are actually using AWS cloud for all this. So basically, in this prototype, we have actually used Blink Cloud, and you can see the Blink app left to my screen and Walkie right off my screen. So yeah, for the vehicle speed, I have to manually move the needle of the potentiometer. As you can see, it is dynamically changing. Yeah, the speed is updating. So yeah, so let me increase the speed and go all the way up to 100 and then cross 150 to get alert. So let's see if the alert is working. As you can see, I have my phone here. Also, you have my phone screen which is displaying left to the screen. So let me increase it. So yeah, 72, 75. 90 so you can see the alert. Yeah, blink. Oh, speeding alert. So yeah, alert is working fine. Yeah, let's see if we get the fuel metrics right when we hit 120 kilometers. Sorry, 1 minute. Sorry. So let me close the app. Cookies online. And our speed is 43 kilometer as of now. Let me try to increase. So let's say it is 68. So yeah, field metrics will show up very soon. And for the fuel, we are actually designing a same the data visualization where we can actually see the fuel uh, graph. So we can actually see the some bending in here. Yeah. Some deflection when the fuel is reduced. And so the latency also matters. We need to have a fuel metrics. So yeah, and we have got a fuel level which is 44.55. So we can see 0.45 liters of fuel is consumed when the vehicle is traveling constantly for the speed of 68 kilometers per hour and have used 1% reduction rate. So yeah, let me see some. So yeah, actually I have kept the fuel metrics visualization which is 5 minutes. So the video is gonna get lengthy. So let's look at our software. I mean, yeah, our website prototype. Next, yeah. So this is our methodology and process of implementation where the user logins with his credentials and verifies himself and proceeds to the next stage. And that's for the website or an mobile app where we build it with the Flutter for mobile app and React.js for website. And for the backend, we are using AWS for user authentication and REST APIs to handle the data between hardware components and our website. So we are coming to the next stage of implementation. It says vehicle connection. So for vehicle connection, we are using two hardware components, which is ESP32 or Arduino. So it's like a basic home of the circuit where we can transmit the data from to and fro to our website. And yeah, vehicle communication. So this is where the smart commute starts. So after the vehicle starts, we get the vehicle status, and we get the real-time location of the vehicle and any other vehicle malfunctions. So yeah, coming to the real-time location, how we are going to implement it. So there is a hardware module which is Neo 6M GPS. We are attaching or connecting it to the Arduino, and we are configuring and transferring the real-time location to our website using APIs. So yeah, that's for real-time location. And for geofence alerts, we are actually setting up virtual boundaries from the website, which can be user defined. Yeah, so as per user requirements, which we are making them able to create the virtual boundaries, so called geofence. So how are we implementing the geofence? So we are using AWS Cloud for the location of the geofence, and front end JavaScript for real-time notifications or alerts. So yeah, and there comes the main part, which is onboard diagnostics. So this is the, say, 40% of the project is dependent on onboard diagnostics. So how are you gonna get the onboard diagnostics? So we have ELM327, which is an OBD2 adapter. It is available in Wi-Fi or Bluetooth communication. We can get the data from the OBD from through Wi-Fi or Bluetooth. So we are configuring the OBD2 adapter according to our needs. So how exactly the OBD2 adapter works? So actually, in mechanical shops or car showrooms, when a car is came to the service, they connect the OBD2 adapter to the OBD port, which is available on the driver dashboard, and they get the faulty codes. So actually, we are utilizing that faulty codes, and we are declaring ourselves like engine malfunction, oil leak, excessive heat, and we are user defining it. Say we are defining it. And coming to the CAN. So what is CAN? So we are using CAN to convert the binary data to the human readable form, where the binary data is thrown by OBD2 adapter and it is converted to human readable form with the help of CAN. And we are using C++ to program it, and we are configuring Neo 6M and OBD2 according to our needs to connect with our website, and we can utilize and we can implement other features. So yeah, and for data visualization, we are using Chat.js, where you can get fuel consumption rate and driver performance. And for the drowsiness detection, we are going to see that very soon. And lastly, we got parallel processing, where real-time location updates frequently and OBD2 diagnostics, say onboard diagnostics of the vehicle. Vehicle diagnostics update parallelly and real-time location updates parallelly. Say that vehicle stopped, vehicle is running, vehicle came to halt at some position, and if any accident occurs, we get the real-time notification. And when vehicle breakdown happens, say we got fleet manager to contact the driver to ask what exactly is the problem occurred in the particular vehicle. So yeah, next slide. So yeah, coming to the impact and benefits. So who are the stakeholders involved in a project? So we got citizens, individual who use daily, individual who travels daily in in the communities. Say they go to gym, college, school, and especially it is very important to implement this system or smart commute, and especially geofence in school kids and also women, uh, by by considering the present factors in the society. Say the women lack safety, and we got geofence for that. And transportation authorities, say we in Telangana we got TSRTC. The depot manager can manage all the buses. They got vehicle diagnostics and live monitoring of the bus and the traffic, and if any. And in our state we actually see many RTC buses breakdowns frequently. So they by that we got traffic issues in the important curves or important circles, and by that the congestion makes more. So yeah, and coming to infrastructure providers, say not infrastructure providers, let's say industrial areas. So he can track the vehicles moving around the constructing area. So for best example, we are taking mining. So mining occurs underground. So this is a mining upper level, and this is a lower level where constructive works. So we create geofence above the mining area. So we alert the mining manager, or yeah, so we take mining manager, we alert when the vehicle enters this area, so that a vehicle doesn't fall on the, say, workers. So yeah, like we know how the land is very thick. And coming to the local communities, and for the best example of local communities, we are taking corporate vehicles or rental cars. So by using our smart commute, they can easily track their rental vehicles, their status, their location, and the uh, amount of distance they travel, and the fuel consumption, etc., etc. Yeah. And impact on the target audience, as I said, live monitoring. Safety is important in our smart commute. We are actually making it as our first priority. And efficiency and cost effective. So as far as we are concerned, we got 500 rupees for geofence. So say geofence is setting up virtual boundaries, that is part of website. So we are using the hardware component, which is Neo 6M module. We can get it, say, 300 rupees, and Arduino 200. Yeah, so we can cover it up 500. So for safety, even citizens can afford 500. Yeah, we are being optimistic for that. And we got a user friendly interface in our website. We are going to get to see that shortly. And social benefits, social. So for the society, we got enhances safety with live monitoring, and economic, it is cost effective, as I said, and environmental, promotes efficient vehicle usage. So yeah, we can restrict our usage according to our needs, according to a daily travel basis. So yeah, coming to the flowchart we have here, uh, we are we got another name, which is fleet management system, where we can we classified it into two different parts, which is commercial vehicles and domestic vehicles. Coming to the domestic vehicles, we have personal user, or say citizen, and coming to the commercial vehicles, we have fleet manager. And the features of the fleet manager are live monitoring and maintenance updates of the vehicles and vehicle diagnostics. And for the personal user, it is only geofence. Also, we can he or she he can decide that whether he want vehicle diagnostics or he want to stick with the geofence for his safety. The common thing for the two categories is geofence. So basically, geofence is particularly the main part, and we are going to get the alerts. So yeah, next. So yeah, coming to the feasibility and viability, we are feasibility analysis by taking help of the APIs. We are processing our data very efficiently, and sensor connectivity. We are optimistic that it supports both 5G and 3G sensors for reliable data transmission. And MCU, which is the battery, we are giving to to power the circuit externally and transmit our data to our website. And challenges and this, so there comes our challenges, which is connection reliability, consistent restoration and maintenance. So how are we going to overcome that? We are consistently updating our module and frequently providing updates to the users to update to the particular sensor or the code or other things the update requires. So yeah, coming to system connectivity, continuous sensor system communication, which is 100%, and hardware functionality, reliable performance of sensors and hardware. We are gonna take A1 hardware components and uh, yeah, we're gonna take the hardware components from the respective companies. Say Arduino have Arduino importer. We are gonna take the main Arduino board, not like the cheap ones which are available in the local market. And as I said, overcoming the strategies, accurate sensors, and enhanced connectivity. So yeah, we are gonna achieve it through Wi-Fi communication. Where in the cities we have Wi-Fi, so we don't require GSM. So for how are we gonna focus in rural areas? So in rural areas, we are gonna use A9G module, which is say GSM purpose. We can insert SIM in that module and we can communicate to our website. So GSM stands for Global System for Mobile Communication. We are inserting SIM and the hardware component does everything. So yeah, over to Kartika.
Yes, thank you. I would like to now give a basic demonstration of our prototype. We have developed a prototype, a basic UI model using Figma. Yes. So this is the main dashboard where it gives a glimpse of all the vehicles. For at present, I've used two vehicles, a two-wheeler TVS and a four-wheeler Kia. This is the list history of the vehicles. The red dot is for indicates that it is stationary, and the green arrow is moving, and the last location. Coming to geofence, we've set one geofence in common, that is home, and we've given a shape in, and it created a boundary. And here are the geofence coordinates location. You can also select the geofence shapes. Now choose asset. As I said, I've given two assets. This is for the asset two-wheeler TVS. I've set the geofence as a college, and I've chosen the color. We can select the shape and all the boundaries. One more is Kia. Yes, we've chosen like this. We've used another shape. Next is assets, which gives the dynamic data, last communication location, the present fuel level, current trip status, current speed. For more details, for the driver details, yes, a vehicle type, vehicle details, chassis number, and other details. Yes. Coming to alerts, as I've said, we have customization alerts option. We have speed monitoring, fuel level monitoring, door status, tire pressure, collision detection, geofence breach, and driver drowsiness. And these are a couple of notifications just for an idea: fuel alert, speed drop, arrival notification, and users who can access the data. So I've included two users and feedback section. Yeah, that's it.
So coming to the drowsiness prototype, we have actually built a model using the DLib library for predicting for tracking our ice shape, where we have declared here a aspect ratio function. And coming to the capturing of the ice, we have used CV2 package, which is used as a CV2.video capture, and we have used SciPy backend. And yeah, let's fill it up.